Hello and welcome back to Network Information Hiding. Today with the chapter number 8 on replicating experiments. Why should we do this? Well, it allows us to validate research, either before it's published or after it's published. And in some sciences, I read this especially about psychology, there were even fundamental results that were available in textbooks for ages discovered to be incorrect and had to be removed from textbooks. They had quite a crisis. So also we can conduct replication studies because this allows to change parameters in experiments, and then we can potentially gain more insights into methods that were developed by other people. But there is a problem because almost nobody seems to replicate experiments. At least not in the covert channel domain, but it's also not too common in the information security domain. And there are manifold reasons, for instance, that it's difficult to publish a replication study because this is not so interesting like a new thing. And often there's also just no data or code available. Also, who has time to conduct replication studies? It's difficult to get this funded and employ people to conduct such studies. And one method to increase the number of replication studies would be to honor replication studies as research contributions. And that could render them more attractive. Also, of course, code and data should be made available, especially code if data can be generated easily, or let's say network traffic can be just recorded in other networks, but the code should be available in any case. I also put quite some code on GitHub, for instance, the code for the null phase that I discussed in chapters 6 and 7b. I will also show you something later that I put on GitHub where you can replicate quite some experiments that I did in the recent months. And one other question is how trustworthy are actually the results that are published or that are reviewed. So as a reviewer, you don't always get all the data, and you check, of course, for plausibility. But if it's plausible, then you think, okay, yeah, it's plausible, but you don't always get the data, and that's a problem. And even if you get the data, who has time to replicate anything? Because most reviewers are just super busy, and I personally reject several program committee memberships basically every month. I reject program committee memberships, especially for big conferences, because there you have to review many papers, and I just don't know when I should do this. Well, what is a good indicator in the end still is the journal and conference quality. If it's a good high quality conference or journal with a high impact factor, then the review is most likely very well conducted. But what is not a good indicator is the publisher name, even if it's Springer, IEEE, ACM, Elsevier, or whatever. I found tons of crappy papers there in the last year's papers. Also, just last week, I saw one paper that published some absolutely trivial method that is known since 20 years and that I would not even assign to a bachelor thesis in some nice Springer conference proceedings with a nice name. But it's I'm sorry to say it, but it's crap. So it's not any research because it's just absolutely trivial, not a new thing. But these things still get published, which is pretty annoying. But well, this is how it works. I guess it's also because the publishers benefit from the conference fees somehow. Anyway, we founded the International Workshop on Information Security Methodology and Replication Studies, taking place the second time this year in 2020, again linked to the ARIS conference, and we accept replication studies. Of course, if they are conducted well, and that means you should make code available and things like that. Also, other topics like taxonomy work, terminology work, methodological work, everything that has to do with science of security can be submitted there. And we also had some journal special issues. One is appearing in the next months at the Journal of Universal Computer Science, where extended workshop papers of last year plus new papers are published. First idea to perform replication studies was the Vodikov framework, Worm's distributed covert channel detection framework, where you can insert either traffic in some form, be it live or captured traffic. Then the metadata is extracted and some parallel detection algorithms are used to see whether there's something, some covert channel in the traffic. However, this was quite a complex system, so I developed a new one, which I'll show you later. But first, let's look at a publication that we did, where we published, where we described the Vodikov test, but also performed the first replication study in network steganography or network covert channel research, namely a paper by Cabuk et al. The early version of the paper was published at ACMCCS, which is a major conference, one of the very best conferences in cybersecurity. And the extended version of the paper was published in ACMTISSSEC journal, which is a very good security journal. The journal version received over 500 citations since then. And in this paper, they published the compressibility metric that I introduced in chapter 7a, and where I performed a countermeasure variation for several times. So we first wanted to know, because the authors in their paper tried to detect interpacket gap channels, which are called SCC and TCC here, and they show that the traffic can be differentiated, distinguished from legitimate traffic when a precision of 3 or 4 was used, but we could not really replicate this too well, actually, because in our case, legitimate traffic was overlapping the kappa scores of the covert channel traffic in many cases, depending on how the traffic is configured. So if we used exactly the same values as they did, it worked rather well, but if the values were slightly different, then values were overlapping. So, well, this was a new insight. And also, well, the tau value is the difference of interpacket gaps. So if a covert channel is configured with tau 0.04, then it either sends a packet at 0.04 or it doesn't, or it sends one at 0.04 to have a 0 bit, or at 0.08, so 2 times tau, to send the other bit. We should get the same value as Cabuk et al. For compressed traffic, because they, as far as I remember, used compressed traffic, and so compressed and randomized traffic is basically the same from the characteristics perspective. So we used 3 compressors, and we got the same result here for tau 0.04. Faust is a German novel by Goethe, which is one of the most, if not the most famous German writer ever, and so we just experimented and wanted to see how the traffic, the kappa value looks if we transfer ASCII traffic or even very, very high redundancy traffic like AB, 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 and so forth. Or the quick brown fox jumps over the lazy dog or something like that. And so for tau 0.04, everything looked fine. But for 0.06 and 0.08, we got slightly different values, which does not mean that the research by Cabuk et al. Is wrong. Maybe we did something wrong, but we just couldn't get the same results. And but still, you could at least use this somehow to distinguish between covert channel and legitimate traffic, partially, because the novel traffic, the novel's characteristics seem to result in the same kappa value as the covert channel traffic here, compressibility score of approximately 7. Then we also, as I mentioned, in replication studies, you can change parameters. We switched from remote to Ethernet, and in Ethernet, we just got highly different kappa scores. Again, it's all right if the original paper says, okay, we did this under these conditions, we used Ethernet or we used remote. I don't remember which one they used, but if you change the parameters, then you see, okay, this compressibility score does not work so well. So I think it's fine if a paper just mentions the conditions exactly, and then it's fine, because you cannot test everything. And every internet connection can also be different. But what this insight tells us is that the connection matters a lot. And we also performed the first work to make a covert channel detection algorithm a parallel covert channel detection algorithm. So on one computing node, this algorithm by Cabuk et al. Took for, I don't remember how many gigabytes of PCAP traffic on the server were computed, but it took 3 hours. And with 2 nodes, slightly more than 50%, which is a super duper speed up. And with 3 computing nodes, we were down at 1 hour 4 minutes, which is really good. So their algorithm is a very nice one because you can make it parallel. I like it. It does not work with all patterns, and not all patterns are studied, but it works well, and it's a good feature also for machine learning nodes. Even if we could not replicate everything, it's still interesting to use. So what I'm working on right now is the Nephias project, Network Forensics and Anomaly Detection System. This is super tiny. Main system contains less than 1,000 lines of shell codes. It's super portable. It's good in terms of performance if you have a Beowulf cluster and many nodes, and it does not require any framework or something like that. It's just shell and AWK. So this works rather nicely. I show you some sample session now. So here's a sample session for Nephias using Kappa's the Cabuk et al. Inter-arrival time. I use a different precision, different rounding, so the values are not exactly the same in this version. It's also different from Vodikov, but I show you the code soon. So what this does is it uses just a localhost node to perform some computations. We take a traffic source. Here in this case, it's the quick brown fox jumps over the lazy dog with a timing channel that uses 100 and 200, I think, milliseconds to signal the hidden bits. And we use the inter-arrival time kappa calculation. Just one node, just a local host, 15,000 packets per chunk, because we split this into chunk that we later compress. And we use these standard values here from the packet. We don't need all of them, but I just didn't remove them. And then these chunks are uploaded to the slaves and they compute the results, and we get the results here in the results directory. I need to make this a real comma-separated value file, so the kappa and win size parameters should just contain the values, of course. This is also another window size than used by Cabuk et al. Because I played around with 1000 here, and we see the different kappa compressibility scores for different connections. So this is just one connection actually split into multiple windows, and I think some of these values are also from an old recording when I ran the test a few minutes earlier, so only 50% are new. This is why the values are exactly the same, and it's one connection with 2 flows, one in this direction, one in the other direction. Let's look at the scripts and into the kappa IIT. This is the script that calculates the compressibility score. So I just use the Nephias library here and say I want TCP flows. And now I can just grab through all the flows, because I can say for flow in flows, grab the flow, get me the first 1001 packets so that I can calculate 1000 inter-packet gaps for the packets. This is and I made it in a way that you can directly in AWK access things like frame time relative or IP source address or TCP port or whatever you want. So this is makes it really easy. I just calculate the relative differences of the packet times here, concatenate them to a string that I output in the end if I have enough packets. I write this in some temporary working file, which is a parameter that comes with Nephias. Then I just compress the file, calculate the string length of the original file and the length of the compressed file. Kappa calculation is just dividing one by the other. And I write the results into the in the results file. So this is all. And Nephias finish cleans it up, and I just remove my temporary files. So this is really easy. If you get used to it, you can write scripts like this in no time. They always follow the stream loop structure. And to sum up, so replication studies can lead to new insights. Even if previous work is not necessarily wrong, replication studies can extend our understanding of how a method performs under changing circumstances. And we should do this more often to understand our research more deeply, especially if it contains measurements.